Good day, students, and welcome to your first lecture of Allen 2016A Electronics 1. I'm your lecturer for the day, Mohammed Dango, and we'll be covering semiconductors. First up, we've got types of material, followed by some semiconductor physics, intrinsic and extrinsic semiconductor, P and N type semiconductor, and we're going to end off with the phenomenon of drift and diffusion currents. Now, please refer to your textbook, Chapter 1, pages 10 to 22, and remember that anything said or done in this lecture can and may be used as a question against you in your test or examination. Now, types of materials, we can have three types: conductors, semiconductors, and insulators, and this is according to their conductivity. And conductivity, as you should know, is opposite to resistance, and it's measured in Siemens per meter. If we look at a conductor is a material that allows for the generous flow of current or charge, and some examples of conductors are gold or copper. An insulator, such as air or rubber, these prevent the flow of charge or current. Very good to be used for safety or protection. And finally, we have the semiconductor, which allows or permits for a moderate flow of charge or current. Now you're looking at this and you're probably thinking, okay, sir, a semiconductor kind of looks like a very shitty conductor or a very shitty insulator. But I'd say to you, perhaps, but a semiconductor has some special properties. And one of them is that it can be doped or changed in such a way that we can change the conductivity of the material. Also, the mechanism of current flow or charge flow within a semiconductor is quite different to that of a conductor, and we'll look at that in more detail later on in this lecture. So the material that are used to create semiconductors come from the 14th group of elements on the periodic table of elements, and one of the most used material for semiconductor materials is silicon. So we're going to use silicon as the element to help us with our understanding of semiconductors. And here we have it, the silicon atom. Now, because silicon is from the 14th group, we know it's got 14 protons and 14 electrons. And of those 14 electrons, we know that 4 of them are valence electrons. Now, if you're unfamiliar with valence electrons, these are the electrons on the outermost shell of our silicon atom. So you can see here we have 1, 2, 3, and 4 valence electrons. And as we move inside towards our nucleus, we have our second shell and our first, which are our inner shells of our silicon atoms. And right on the outskirts, what you see here is known as the conduction band. Now the conduction band, you see no electrons there, but a valence electron from the valence band can get sufficient energy and break out of this valence band and move into the conduction band. So let's take a look at that. Here we have the energy band theory. Again, we have our silicon atom, the two inner shells, which is the first and second band. You can see their band energy is quite low. And then we have the valence band, which is the outer shell containing our 4 valence electrons. And finally, the conduction band, which between the valence band and conduction band, we see what is called a forbidden band gap. And that forbidden band gap basically means that you won't find any electrons in the space. And in order for a valence electron to move out of this valence band and into the conduction band, it needs a certain amount of energy. If it doesn't have that energy, it's not going to happen. And for silicon, we know that energy is 0.72 eV. Now this is a nice point to end off on types of material, because now if we look at a conductor and we see the valence band versus the conduction band, there's basically no forbidden band gap between them, which means that electrons can move freely between the two, allowing for the generous flow of current. In a semiconductor, as we've seen, there is a moderate forbidden band gap. And this does allow for some valence electrons to move into the conduction band, and that's why we see a moderate flow of current. And finally, the insulator. It's got an absolutely massive forbidden band gap, up to 7 eV, and that's why it's such a good material to prevent the flow of current or flow of charge. All right, ladies and gentlemen, the semiconductor crystal lattice. If we take silicon atoms and we condense them to form a solid, they form what is called the crystal lattice. So if we focus on the center silicon atoms, you will see that we have our 4 valence electrons, and then we have another 4 valence electrons which is shared with the neighboring silicon atom. So we can say that a silicon atom in the crystal lattice has 8 free valence electrons in total, and 4 of them are its own, and 4 of them are shared with its neighboring silicon atom. Now, when these valence electrons come together, it creates what is known as a covalent bond, and this covalent bond basically sticks our silicon atoms together. And if we want to visualize that a bit better, looking at the actual atoms, this is what it looks like. Again, focusing on our center silicon atom, we still have our first band and second band. They didn't go anywhere. We're just illustrating them here. And in the valence band, here we have the shared valence electrons with our neighbors, and of course the covalent bonds. Right. Now, something very interesting takes place within the semiconductor crystal lattice when it is at room temperature or slightly above room temperature. Because you see, what happens is at this temperature, some energy can be imparted into a valence electron. And this causes the silicon lattice to literally vibrate, and this silicon valence electron gets enough energy to break the covalent bond and move from this valence band out into the conduction band. And the electron is then known as a free electron once it is in the conduction band, and it has a negative charge, so it's called a negative charge carrier. But something else seems to happen. So when this electron gets enough energy, breaks the covalent bond, and moves into the conduction band, it leaves behind what is known as a hole. And because the free electron has a negative charge, it's only the same to have the hole having a positive charge. So our hole is known as a positive charge carrier. Now, this process of electrons breaking out of the valence band and into the conduction band is happening continuously at room temperature within our semiconductor lattice, and this is called electron-hole pair generation. So once our electron-hole pairs are generated, we can actually see that there's a movement that takes place. And if we look at our electrons, you know they are negative charge carriers. That's why there's a lovely negative sign there. And our holes are positive charge carriers. That's why we've got this lovely positive sign there. And as you know, opposites attract. So our negative electron or free electrons are attracted to our positive holes. And this causes our free electrons to then move into and fill a hole within the valence band. So basically, you can think of it as if I am a free electron in the conduction band, any hole is a goal. And that is how I move through the crystal lattice to wherever I want to go. But note, even though the electrons are moving, the holes are also moving in the opposite direction. And this movement is known as electron-hole pair movement. Now finally, when an electron fills a hole, it's known as electron-hole pair recombination, and that basically just means exactly what I've said. A positive charge carrier is attracted to and fills a negative charge carrier, is attracted to and fills a positive charge carrier, which is the hole. And that is electron-hole pair recombination. Now, you're probably familiar with the fact that a flow of electrons causes current flow. or is current flow? And you'd be right. So let's look at current flow in a semiconductor. Here we have a semiconductor and I've plugged on a battery, positive terminal, negative terminal, onto our semiconductor. And what this battery does, students, is it sets up an electric field within our semiconductor, illustrated by these gray lines. And this electric field then causes the flow of electrons, which is in the opposite direction to the electric field, and the opposite direction of conventional current flow into the positive terminal of our battery. And our holes, they move in the same direction of this electric field and in the same direction of conventional current flow into the negative terminal of this battery. And students, this is where one of the big differences between a semiconductor and a conductor can be viewed, is that the flow of current in a semiconductor is caused by two charge carriers, the flow of electrons as well as the flow of holes. Whereas in a conductor, the flow of current is caused by only the flow of electrons. And that is a major difference between the two materials. And also, this is how we can go about changing the conductivity of a semiconductor by changing the number of holes and electrons that are present. And we'll get to that a bit later. But first, I'd like us to visualize this electron and hole flow within the lattice. So looking at the hole flow, we see our holes are moving in the same direction as the electric field, but also notice that the holes are only moving within the valence band. Look at that, they are all moving within the valence band. So hole flow takes place within the valence band, whereas free electron flow, which is in the opposite direction to this electric field, this is taking place, students, in the conduction band. So important to note that hole flow takes place within the valence band and electron or free electron flow takes place within the conduction band. So now that you're very familiar with the semiconductor material and the flow of current, holes, free electrons, it's a good point in time to introduce different types of semiconductors. Yes, so we have intrinsic or pure semiconductors and we have extrinsic or doped semiconductors. Also, with our extrinsic or doped semiconductors, we have two variants, the p-type or trivalent and the n-type or pentavalent extrinsic semiconductor. If we take a look at the intrinsic semiconductor, students, you're familiar with this. You've seen this picture before in an earlier slide. An intrinsic semiconductor is one composed of elements that only have 4 valence electrons, such as this silicon lattice over here. So as you can see, all of our electrons are within our valence band, and this is a pure semiconductor known as an intrinsic semiconductor. There's also an equation that can be used to calculate the intrinsic carrier concentration, basically the concentration of silicon in the semiconductor. And that's equation 1.1 that you see over here. And a lot of the terms in this equation, such as the semiconductor coefficient, the temperature, Boltzmann's constant, the band gap energy, these terms will be provided to you. So let's illustrate this or look at this equation in action with an example. Calculate the intrinsic carrier concentration in gallium arsenide and germanium at a temperature of 300 Kelvin. And there we see the equation. And here we are. Students, here's the solution. So basically we look at table 1.3 in our textbook and we can get these unknown terms Eg and B. Temperature was given and the intrinsic carrier concentration for gallium arsenide and germanium can then be calculated. 1.8 times 10 to the 6 and 2.4 times 10 to the 13. All right, and that's it, guys, for intrinsic semiconductors. Looking now at extrinsic semiconductors. On this slide, we are looking at what are known as dopants. So, what is a dopant? For a p-type or trivalent extrinsic semiconductor, the dopants are aluminium, boron, or gallium. And you've probably figured it out by now. Trivalent means 3 valence electrons. So our dopant has 3 valence electrons. And basically what we do is we replace a silicon atom in our semiconductor material with this trivalent boron atom, and that creates a p-type semiconductor. Similarly, for the n-type semiconductor, we use pentavalent elements such as phosphorus. Here we have 5 valence electrons, and we replace the silicon atom within our semiconductor with a phosphorus pentavalent atom, and that creates an n-type semiconductor. Other examples of pentavalent materials or elements that can be used are arsenic and antimony, and for trivalent, other examples are aluminium, or if you're American, aluminum and boron. So what does this actually look like in the crystal lattice? Here we are, extrinsic semiconductors in the crystal lattice. Here we see for our p-type or trivalent, we have replaced the center silicon with a boron, and would you look at that, it has a hole, because we know boron only has 3 valence electrons. That means the space where there was a 4th valence electron is replaced with a hole. And because of that, this boron atom is known as an acceptor atom or an acceptor impurity, because it has a hole which is a positive charge carrier that can accept a free electron that is somewhere in the conduction band. For our n-type pentavalent, we have replaced our center silicon with phosphorus, and look at that, we have an extra free electron due to this, because our phosphorus has 4 valence electrons and a 5th valence electron which can't go into the covalent bonds, so that 5th valence electron ends up here in the conduction band. So because this phosphorus atom donates a free electron to the crystal lattice, it is called a donor atom or a donor impurity. Excellent. I'm sure that was very easy to wrap your heads around. But let's look at this in a bit more detail. This is an important slide, students, because it takes you through the terminology and the key that I'll be using moving forward in my lectures to explain p-type and n-type semiconductors. So starting off with the p-type trivalent semiconductor, our holes are known as the majority carrier. But why? Well, students, that's because if we look at this, there are majority holes compared to free electrons in the crystal lattice. So because there are majority holes, the holes are known as majority carriers. The free electrons, there are less of them. They are here, you can see them. And because there are less of them compared to the holes, they are known as minority carriers. And finally, the actual atom of boron that was put or doped into this intrinsic semiconductor, that is known as an acceptor ion, because it can accept a free electron charge. Looking at the n-type pentavalent, we now have holes which are the minority charge carrier. Yes, students, look at that. Much less number of holes compared to free electrons in an n-type semiconductor. And of course, because there's a lot of free electrons, quite a few, look at them. Can you see them? Yes, you can, unless you're blind. The free electrons are the majority carrier. And finally, because these phosphorus or pentavalent atoms are providing a free electron to the crystal lattice, they are known as donor ions. Take some time to wrap your head around the slide. This terminology and key will be used quite a bit moving forward. Now, the next thing to look at is, for our extrinsic semiconductors, how does current actually flow? Because we know in a semiconductor, current flow happens due to the movement of 2 charge carriers. So in a p-type semiconductor, the current flow is due mainly through the movement of holes. And for an n-type semiconductor, the flow of current is mainly due to a flow or movement of free electrons. And that makes sense because in a p-type, holes are the majority carrier, and in an n-type, free electrons are a majority carrier. Now that does not mean that there are not minority carriers present. Look at the p-type, there are electrons or free electrons present. And look at the n-type, there are holes present, and those minority carriers are also flowing. However, the majority of flow is due to the movement of the majority carriers. Now, an equation to put it all together. The relationship between free electron and hole concentrations in a semiconductor at thermal equilibrium is given by equation 1.2. And we can see that for a p-type semiconductor, the acceptor concentration, which is noted by capital Na, if the acceptor ion concentration is much greater than the intrinsic carrier concentration, then we can assume that the concentration of holes is approximately equal to the acceptor concentration. And that's how we then calculate the concentration of holes. Therefore, once we have the intrinsic carrier concentration and now the concentration of holes, we can calculate the concentration of free electrons. So using this equation 1.2, we can use it to calculate concentration of free electrons, holes, or even the intrinsic carrier concentration. The same equation can be used for an n-type semiconductor. However, in this case, we are not looking at acceptor concentration. We are looking at donor concentration, ND. So if the donor concentration is much greater than the intrinsic carrier concentration, then we can assume that the concentration of free electrons is approximately equal to the donor concentration. Therefore, the concentration of holes can be calculated by simply rearranging equation 1.2. Now then, apologies, let's see this in action. Exercise. Calculate the majority and minority carrier concentrations in gallium arsenide at a temperature of 300 Kelvin for, firstly, a donor concentration of 2 times 10 to the 16. So, if we recall, the intrinsic carrier concentration of gallium arsenide calculated in exercise before this was 1.8 times 10 to the 6. So, compare the intrinsic carrier concentration to the donor concentration, 10 to the 16 versus 10 to the 6. It's very clear that ND is much greater than NI. Therefore, or then, we can approximate the electron concentration to be equal to the donor concentration, and therefore we can calculate our hole concentration, which is 1,62 times 10 to the minus 14. And because this is a n-type semiconductor, we have more donor than holes, and we can see that the free electrons, which are at 10 to the 16, are the majority carriers, and the holes, which are 10 to the minus 4, are the minority carriers. For the second part, we have an acceptor concentration of 10 to the 15, which 10 to the 15 is much greater than 10 to the 6. Therefore, we can estimate our hole concentration to be approximately equal to our acceptor concentration. Therefore, we can calculate our electron concentration, 3.24 times 10 to the minus 3. Right. Now that we've gone through some of the equations on concentrations and the type of materials and the physics of the semiconductor material, we can end off with the phenomenon of drift current and diffusion current. So starting off with drift current, ladies and gentlemen, you are familiar with this. Drift current is basically the movement of charge carriers caused by an electric field. So looking at this beautiful picture that I've drawn before you, we have a sexy little battery over here connected onto a semiconductor, positive terminal, negative terminal, and this battery establishes an electric field, these gray lines, within our semiconductor. Now, of course, this electric field is going to cause a flow of electrons and a flow of holes. Flow of electrons is in the opposite direction to the electric field, the opposite direction to conventional current, and into the positive terminal of the battery. And the flow of holes, same direction as the electric field, same direction as conventional current, and into the negative terminal of the battery. So very simply put, drift current, or the phenomenon of drift current, is the movement of charge carriers caused by an electric field. Now, when these carriers or charge carriers are moving in this electric field, they have what is known as a drift velocity. And we can calculate our hole drift velocity and our electron drift velocity by equations 1.3 and 1.4 respectively. Very easy equations to use, as you'll see in the exercise coming up. Now, once we calculate our drift velocity, we can then calculate our drift current density using equations 1.5 and 1.6, which require you to substitute your drift velocity into them. As you can see here, our drift velocity has to be substituted in, and because our drift velocity we know is a negative here for electrons, this ends up being a positive term. Right then, now that we know our drift current density for both holes and electron, we can have our total drift current density, which is equation 1.7, and it's simply summing the drift current density of the electrons and the holes. And we can make this equation look a bit more sexy by putting in the conductivity, which is represented by equation 1.8, and I'm sure you know the resistivity, which is equation 1.9, is 1 over your conductivity. And that, students, is total drift current density. And we have an exercise for that. Consider an N-type gallium arsenide at T equals 300 Kelvin, doped to a concentration of donors 2 times 10 to the 16. So because there's donors, we know this is an N-type. Oh, they did mention that. My bad. And assume a mobility values of 6,800 for our electrons and 300 for our holes. So, first part, determine the resistivity of the material. So for an N-type, we can calculate this. Resistivity is 1 over conductivity, and we simply substitute in what we know for conductivity. It's the concentration of donors. Plug and play, and we have our answer. Now we can omit the formula for the acceptor concentration because it's negligible, since this is an N-type and the majority concentration is from our donors. Second part of this exercise, determine the applied electric field that will induce a drift current density of 175 amps per cm squared. Take our equation and we replace conductivity with 1 over resistivity. Multiply both sides by resistivity so we can make the electric field the main part of this equation, and then we have our resistivity and we have our drift current density. Plug and play, students, there is your answer. This would make a very nice MCQ question. Keep that in mind. That brings us to an end for drift current. Next up we have diffusion current. Now the phenomenon of diffusion current is basically the movement of charge carriers due to a concentration gradient. I'm sure you are all familiar with diffusion by now in your lives, and if you aren't, well, you're going to learn something today. So diffusion occurs when there is a concentration gradient. For example, in an N-type semiconductor, if we have a bunch of free electrons on one side and very few on the other side, this creates a concentration gradient. And we know that things like to move from a high concentration to a low concentration. And when this free electrons start moving from a high concentration to a low concentration via diffusion, that movement generates our diffusion current. Note that this current is being generated without any external supply to our semiconductor. So we have a current called the diffusion current that's been generated without an external supply. Now similarly, in a p-type semiconductor, we have a large concentration of holes on this side and a low concentration of holes on this side. So from a high concentration, it's going to diffuse to the lower concentration. That movement of charge carrier, specifically the holes, is going to generate our diffusion current, which is in the same direction as the movement of the holes, and that is our diffusion current for a p-type semiconductor. And eventually, once the diffusion takes place, you can see that we now have a much better spread of our free electrons and of our holes inside our semiconductor materials. And that, students, is lecture 1 for you. To recap, on our end slide, we looked at types of materials according to their conductivity. We had conductors, semiconductors, and insulators. I explained that semiconductor has a different mechanism for the flow of current compared to a conductor, and that we can alter the conductivity of a semiconductor by doping it. I took you through some semiconductor physics where we looked at the crystal lattice and we went into the electron hole pair generation, movement, and recombination. We then looked at intrinsic and extrinsic semiconductors, intrinsic being crystal lattice that is formed from only the 4 valence electron elements, whereas extrinsic semiconductors, the p-type is doped with a trivalent element and the n-type is doped with a pentavalent element. With an intrinsic semiconductor, or rather with a p-type semiconductor, we see that the majority charge carrier are holes, the majority charge carrier are free electrons. And in an n-type semiconductor, the majority charge carrier are free electrons and the minority charge carrier are holes. Finally, we went through diffusion and drift currents, and we know that a drift current is due to an electric field that causes a movement of charge carriers, and a diffusion current is a movement of charge carriers caused by a concentration gradient. Students, if there's anything you didn't understand, please refer to your textbook, chapter 1, pages 10 to 22. Take some notes, bring them to the lecture enrichment session on Thursday. I'd be happy to answer any of your questions, and I hope you enjoyed this first lecture to LN 2016A Electronics 1 course, and I look forward to lecturing you for the rest of the semester. Thank you.